Welcome back to Share Science. I'm Curie Fox.
And I'm Derek, here for the week of March 30th, 2026. We've got 5 stories, 0 jargon, all in This Week in Science.
Okay, so get this. A single fossil found in Egypt might just rewrite the entire story of human evolution. That's how close it is to the common ancestor of all modern apes, including us.
That's a pretty bold claim. I mean, how often does a single discovery like this actually change the narrative?
Well, it's rare, but when it happens, it's monumental. This fossil, named Mazrapithecus, is estimated to be 17 to 18 million years old. What's fascinating is that it's right at the evolutionary branching point where humans, chimps, gorillas, and orangutans all started to diverge.
So, it's like finding a snapshot of the family tree at the exact moment it starts to split.
Exactly, and the fact that it was found in Egypt is a big deal. Most of the research on early primates has focused on East Africa, so this discovery shifts the focus northward and adds a whole new layer to the story.
What does this fossil actually look like? Is it more ape or more human?
It's a mix of both. The skeleton has some very primitive features, but there are also hints of traits that would evolve later. It's not a dramatic missing link like you'd see in a movie, but it's a crucial piece of the puzzle we didn't have before.
And how does this change what we thought we knew about human origins?
It challenges the idea that East Africa was the sole cradle of primate evolution. This fossil suggests that the story is more complex and geographically diverse than we previously thought. It's like adding a new chapter to a book you thought you'd already read.
If someone wants to dive deeper into this, what should they search for?
Look up Mazrapithecus fossil Egypt 2026. It's a fascinating read, and the implications are huge. Now, let's move on to something that feels straight out of a sci-fi movie. Lab-grown organs.
Oh, you mean the lab-grown esophagus? This one really caught my attention. Researchers at Great Ormond Street Hospital and University College London have successfully transplanted a lab-grown esophagus into a patient. And here's the kicker. There was no rejection.
That's right. This is a groundbreaking moment in medical science. Normally, when someone gets an organ transplant, their immune system sees the new organ as foreign and attacks it. To prevent that, patients have to take immunosuppressant drugs for the rest of their lives.
And those drugs come with some serious downsides, right? Like a higher risk of infections and even cancer?
Exactly. Plus, they can cause kidney damage and other long-term health issues. But with this lab-grown esophagus, those problems disappear. Because it's made from the patient's own cells, the immune system recognizes it as self. No rejection, no need for lifelong medication.
That's incredible. How do they even grow an esophagus in a lab?
It's a complex process. They start with a scaffold, which is like a structural framework. Then, they seed it with the patient's stem cells, which grow into the different tissue types needed to create a functional esophagus. It's a huge challenge because the esophagus has to handle things like acid and coordinate swallowing.
It's like a perfect blend of engineering and biology. If someone wants to explore this further, what should they search for?
Try Lab-Grown Esophagus Transplant, UCL, Great Ormond Street, 2026. This is a game changer for organ transplantation and could pave the way for other lab-grown organs in the future. Speaking of game changers, let's talk about solar panels breaking efficiency records.
Yeah, this one had me doing a double take. How can a solar panel produce more energy than the sunlight hitting it? Isn't that against the laws of physics?
It does sound impossible, but it's not. The key is a process called singlet fission. Traditional solar panels use one photon to generate one electron. If the photon has more energy than needed, the excess energy is wasted as heat. That's why traditional panels max out at about 33% efficiency.
That's the Shockley-Queisser limit, right? The theoretical cap on solar panel efficiency?
Exactly. But with singlet fission, certain materials can take a high-energy photon and split it into two lower-energy excitations. This effectively doubles the harvest from that photon. So these new panels can achieve 130% efficiency, not by creating energy out of thin air, but by using the energy more effectively.
That's a huge leap forward. If this technology scales up, it could completely change the economics of solar energy.
Absolutely. It could make solar power far more efficient and cost-effective. If you're curious to learn more, search for Spin Flip Solar Singlet Fission Efficiency 2026. It's a fascinating development. Now, let's shift gears and talk about something a little more cosmic: exoplanets.
Story 4. Astronomers have created a short list of 45 exoplanets that are the best candidates for finding alien life. What makes these planets so special?
They're rocky, located in the habitable zone where liquid water could exist, and close enough to Earth for us to study their atmospheres with next-generation telescopes. These are the planets we'll be focusing on in the search for biosignatures.
Why does proximity matter so much when it comes to studying exoplanets?
To detect biosignatures, like oxygen, methane, or water vapor, you need to separate the planet's light from its star's light. The closer the planet is, the easier that becomes. These 45 planets are our best bets for finding signs of life within the next decade.
That's mind-blowing. If we find even one planet with biosignatures, it could change everything we know about life in the universe.
Absolutely. If you want to dive deeper into this, search for 45 Exoplanet Habitability Shortlist 2026. It's an exciting time for astronomy. And speaking of breakthroughs, let's talk about our final story: Alzheimer's research.
This one's about lecanemab, right? It's the first drug to actually slow the progression of Alzheimer's instead of just masking the symptoms.
That's right. But until recently, we didn't fully understand how it worked. We knew it cleared amyloid plaques in the brain, but we didn't know why it succeeded where other similar drugs failed.
And now we have an answer?
Yes, researchers discovered that lecanemab works by flagging amyloid plaques and handing them off to the brain's immune cells, called microglia. These cells then clear the plaques. The key is a part of the antibody called the Fc fragment, which triggers this handoff.
So now that we know this, what's next for Alzheimer's research?
This discovery opens the door to designing better drugs, ones that are more potent, have fewer side effects, and might even be available in oral forms instead of infusions. For the 55 million people living with Alzheimer's worldwide, this is a huge step forward.
5 stories, and every single one feels like it could change the world.
That's the beauty of science. It's always pushing boundaries and challenging what we think we know.
If any of these stories made you want to learn more, then we've done our job.
Until next time, stay curious, everyone.
See you next week.